Hello. In the previous part, if you remember, we played a role of data guts. So previously we were in the position in which we were able to generate as many observations as we only want. Yeah, and in this part we will turn to a much more realistic scenario where we have finite number of observations, yeah, and using a method which is called validation approach or extension of this cross-validation approach, we will try to evaluate goodness or fitness of several models of different models outside our training sets. And again, training sets are those data sets that are used in the estimation procedure. Yeah, so that's the plan for this part. Yeah, and in this exercise we're gonna follow chapter 5 from an amazing textbook that I mentioned before, Introduction to Statistical Learning with R. Yeah. Here you can find this cover of this textbook, yeah, and most examples that I'm gonna use in next parts also come from this textbook. This textbook is, I think that this is the best introduction to statistical learning, yeah, on the market right now, yeah, and this is it. Yeah, here we will need to load this library, Introduction to Statistical Learning in R. Yeah, and you can you have to most likely you will have to install this using install packages. Yeah, I already installed this. Yeah, and now there is dataset auto from this package. Here you can see, and in particular we will be interested in building the model, the best model. So here this data set has 392 observations and 9 variables. Yeah, and we will want to build the best model that explains miles per gallon, how many miles we can drive, and our function will be horsepower. Yeah, horsepower, but we will be a sort of agnostic about functional specification, and then we will consider many polynomials, and that's the plan here. As I said before, we want to have the model that explains miles per gallon as a some function of horsepower. Yeah, and at this moment, before we discuss what's the nonlinear relationship between horsepower and MPG, let's estimate the simplest model. Here we have MPG, which is function of horsepower, and data is auto. Okay, we estimated our model. We should do it this way, that we assign the result of LM to LM feed, to some object. I call this LM feed, yep. So now, if we want to compute, and in this estimation procedure, all 300, once again, we use all 392 observations. And now, if we want to compute, MSE on this training set, we should do it something like this. We can use predict LM feed. So if we don't, so we want to make prediction using this model, and if we don't provide any additional arguments, then by default those observations that were used in estimation procedure will be used for prediction. Yeah. So here, if we it makes prediction, the length of this is 392. Yeah, and so here, this is our prediction. MSE, yeah, you can find MSE down there, and in our application it should be auto mpg minus, we raise those guys to the power of 2, and we compute mean. Yep. So here we see that this is our measure of goodness of fitness of our model, but the problem is that here we evaluate the quality of fitness using those observations that that were used in the estimation procedure. One very simple way to circumvent this problem is to use so-called validation approach. Yeah, that here, so before, as I said, we used all observations, 392 observations, and in validation approach, we split our whole data set into two parts: training set and validation set. Yeah, and we split our data set in fully random way. The illustration of this validation approach, you can find down. Yeah, this illustration is from the textbook. Yeah, and basically, yeah, we split our data set into two. Here in this illustration, we split into two equal parts. Yeah, and now let's do this. Yeah, in R. Yeah, because we know all commands yeah, we know all commands that we have to use in this to perform this validation approach. Yeah, and so here we can, if splitting the data set into validation and training set is random. Yeah, so if you want to have exactly the same results as I have, set the same seed, and then we can create, we can sample half of observations to be training set. Yeah, and the remaining half would be our validation set. Yeah, half over 2 is 996. Yeah, so we want to sample from those numbers that that indicates rows, and we sample 196. And if one observation is drawn, we cannot draw it again. Yeah, so here it will be false, replaces false. And here now, after using function sample, we generate a vector of those observations that should be included in the estimation procedure. Yeah, and yeah, so yeah, length train, it won't be surprising that it's exactly 196. How to use only those observations that we chose here by sampling how to use only those observations in the estimation procedure? Yeah, it's not very difficult. Yeah, and here, let's create LMFit 0, and this is the model that we use where we use all observations. If we want to estimate the same model, and let's call it valid 1. If we want to estimate this this only with observation with rows, we want to. So here in this data frame auto, we want to choose only those rows that are in this vector. Yeah. So here we can type this and comma. This refers that we want to include all columns in all columns. Yeah, here we need only those 2 columns here, but as data that data that is available to function LM, we provide all columns and only those rows that are in this vector train. Yeah, that's the first. Method. And here actually summary. We estimated this model, and actually with to compare. Notice that LMFit, this is the model with all observations, and we use different data sets, so those they are quite similar, those estimates, but they are not exactly the same. Yeah, and always, if we chose if we chose different observations, those estimates will be slightly different. And this is generated by this this uncertainty that we cannot eliminate. And so here we estimated this model LMFit using only, if we type now predict for the first model, we will have prediction for all observations and all observations that were used in the estimation procedure, and the length is 392. If we do similar thing, here we have only 196. Yeah, and so we use only those observations. Alternatively, exactly the same thing. Let's call it 0. Exactly the same thing can be achieved by using function subset, option subset from LM. Here it is in the documentation. Yeah, here it's this option says that if we provide this optional vector with row indices of observations that we want to include, then we will get something like this. Notice that here it is vector, yeah, and we don't use this square bracket notation. We don't use comma, yeah, and this is it, yeah. So fit valid 0, 1. Yeah, those estimates are exactly the same. Why they are exactly the same? Because both methods, both approaches are equivalent to each other. Yeah, so this is one way to show that both approaches are essentially the same thing. Now we are interested what's the MSE of this model valid, but we want to compute this measure on those points that weren't used in the estimation procedure. Yeah, and so here, if we type something like this, we will get predictions for those observations from the training set. And if we want to, one option of prediction is that we can provide that if as a second argument we can provide data frame of similar or of the same type as the training set. By the same type I mean the same set of columns, and then command predict will make a prediction for those points and not for our training set. So now, how to refer to all those points that are not used in the training procedure, in the estimation procedure? Recall that before we discussed about this. If we want to get rid of one element, for instance, if we want to, the length of this vector is 10. Yeah, if we want to if we want to obtain all elements except the very last, let's say, we can use minus. And here, this is the whole vector, minus 10. It tells us that yeah, the very last element is dropped. And if, yeah, we discussed this before, yeah, but this is just a reminder. If we want to eliminate more than one element, yeah, then we have to use this vector C, yeah, create vector, and then in front of this vector put minus. If I type something like this, then it will drop the second element. This is the second element, and the 10th element, the last element. Yeah, yeah, and here 12 and 20 were dropped. Why I'm telling about this? Because using exactly the same trick, we can put minus in front of train. Yes, so it will tell R to use all rows from data frame auto except those that are listed here. Yeah, so this way we will make prediction on all those observations that were not used in the estimation procedure. Yeah, and now if we want to, again, the formula for MSE is down there. It should appear right now. And if we want to compute this formula, we can actually, let's skip this assignment. Here we don't need this. Here we can compute. Yeah, so this is our prediction. And now we want to take auto MPG minus. Yep. And if we do this way, we will get a result that is not correct, because here we want to subtract from MPG that are not used in the estimation procedure prediction for those observations. Here we get some result, which is not error message, but the problem is that here we use all observations. Those observations are the length of those of this vector is 392, and here it's only 196. So we don't get error message that we subtract from two different from object of two different lengths, because this vector is the length of this vector is twice as large of this. So I don't know whether you remember this from our discussion about using vectors in R. If we have something like this, this is vector of length of 4, this is vector of length 2. This is possible in R, because actually this is equivalent to this. This is what R does it for us. And if this replication wouldn't be possible, and here, if we type like this, it is the length of second vector is not a multiple of the length of the first vector is not multiple of 3. So we get error message here also. It would be nice to have this error message, but we have to be very careful. So this is only to tell you to remember about this. That it is very often there are many situations that you may overlook this, unfortunately. But this is how R is constructed. So now we want to take only those observations which were not. We want to take all values of MPG for those observations that were not used in the estimation procedure. Notice that this object is now, if we use $sign, this is vector. So here, if we want to get rid of all those to use only those observations that were not used in the estimation, we use minus trained without comma, because this is vector. And this is it. Now we have to raise to the power of 2 and compute mean. This way. This is our measure of this is our mean square error for validation points. Also, what is worth mentioning at this point is that those points that this is typical for validation observations, that those observations, that MSE for those observations should be higher on average than for those for which this model was estimated. Now let's test which model is the best. And we will consider the model that we estimated where horsepower depends on that MPG depends on horsepower in a linear way. Also, we will consider polynomial of degree 2 and 3. And how this can be done is that here we will estimate model valid square, and here we can use essentially a function that we already know. This is it. We use subset in this way. Yes, the other option still would be fine, and cubic. Yeah, we estimated model with polynomial of degree 2 and degree 3. Yeah. To evaluate MSE for those two new models, we can recycle our previous code, and essentially the only thing that we have to change is that if we want to have MSE for the model, for this model, it's enough to change predict argument. Yeah, all other things will be exactly the same. And with cubic, it's here. Okay. Yeah, so let's see. This is validation error for a linear model. This is the validation error for quadratic model is lower, and for cubic with polynomial of degree 3 is even lower. Yes, so according to this criteria, the best model would be this with cubic polynomial, yeah, of horsepower. That being said, this method can vary quite a lot, especially for very small data sets. Notice that here we have less than 400 observations, yeah, and that selection of those observations can affect quite substantially our conclusion. So right now, for instance, if we repeat the whole exercise, but with seed equal to 2, before our seed was 1, the same thing, but with seed equal to 2. Let's compute this. Okay, and now we selected we split our data set to training set and validation set in different way, and here we see that, yeah, still square this polynomial of degree 2 is better than a linear model. Before, the polynomial of degree 3 was the best one. And now you see here for new split to validation and training set, we draw a different conclusion. Yeah, so we have to be aware that when we use the traditional, the standard validation approach, this may become an issue, especially for small data sets. Yeah, and we will try to solve this problem using cross-validation that tries to address this issue. Yeah, and we will discuss this in the next part of this lecture. Yeah.